All right, guys, today we're going to be continuing our discussion on equilibrium as it pertains to reversible reactions. And the subtopic today is Le Chatelier's principle, a French guy, Le Chatelier. But if you want to be a good American, you just call him Le Chatelier. But it's his principle that's going to help us to predict which way a reversible reaction will shift. Remember, a reversible reaction goes forward from the reactants to products, but then also it goes in reverse from products to reactants. I don't know if you guys watch Charlie Brown. When Charlie Brown's teacher gives a written test, wah, 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 wah. If you don't watch Charlie Brown, you know what I'm talking about. Best time to study is between yesterday and tomorrow. That would make it today, right now, guys. Best time. Okay, you can tell it's a reversible reaction. You see the double arrow?
Once the system is at equilibrium, the concentrations or amounts of the products and reactants.
Okay, so this is showing two ions. We have a positive ion and a negative ion combining together to form this compound here. And so these can collide and react and form the product, but at the same time, this product, those product species can collide and then break up back into this. And eventually, right, you can imagine if we start with our reactants, the forward reaction is going to initially be the fastest, right, because that's all we have. But then as the product builds up, now there's more and more product that can collide together. And so what happens is the reverse reaction begins to speed up. And then as the reverse reaction is slowing down, as this is getting used up, eventually you're going to reach a point at which the rate of the forward reaction is equal to the rate of the reverse. So you got just as much going this way as is coming this way. And so what's the result? These stay constant. And we would say that reversible reaction is at equilibrium. Okay?
Yes, but it doesn't mean that there's an equal amount of products and reactants. Only that the rates of the forward and reverse reactions are equal.
And you guys, going from the past lesson, remember we could predict which side is favorable. Is the reactant side? Are we going to end up at equilibrium? Are we going to end up with a greater concentration of reactants or products? And you remember we can do that by looking at the K value. Remember, that's the equilibrium constant. If you have an equilibrium constant greater than 1, that would indicate that the product side is favored. If you have one less than 1, it would indicate the reactant side is favored.
This balanced state is called equilibrium, and it's shown with double arrows. Let's look at a particle view of this reaction in our virtual laboratory.
Okay, so you guys, here are our reactants we're starting with. And they're trying to make it simple. They're saying like this would maybe appear yellowish, this would be white, and then right, those can collide together and form iron thiocyanate. So we have iron ions, thiocyanate ions, and the iron thiocyanate. What you guys see when they're together, it would make it red. You see what we're starting with? We're initially starting with our reactants. So we're starting with reactants. Remember, due to random molecular motion, they're going to just be moving around and they're going to collide. If they collide with enough energy, they can combine together to form our product. So let's see what it would look like.
Wow!
Woo!
The reactants collide to form the product.
So some of them are coming together.
All the reactants don't become products. That fits with our observations.
But some of the products are splitting apart to become reactants, even as more products are made. This is a reversible reaction.
Notice that in our small sample, at any time there is about the same number of product particles.
That's right. When a balance is reached, the forward reaction is proceeding at the same rate as the reverse reaction.
Guys, this is taking place in an aqueous solution, just like in a solution. So these are dissolved in water. And so in a sense, that's a closed system because they're kind of trapped in that aqueous volume. So some of the yellow and white were combining together to form the red, but at the same time as that's happening, some of the red molecules are colliding and dissociating back into the yellow and white. So you can see even at equilibrium, we have all of the reaction species present. Okay, so that was kind of a review of equilibrium in general, but now we're going to go into what's called Le Chatelier's principle. And he did experimentation and recognized that when a system experiences a stress is a change, you change it somehow, it will adjust if it can to minimize the stress. Okay, I know it's kind of hard to understand, but we'll try to help you understand that here in the next few minutes. What we're saying is it makes it seem as though there was less of a change than it really was. So it's going to shift. The equilibrium is going to shift in such a way to minimize the change. Okay. Okay, so you guys, we're going to look at two types of reactions here. So you guys write these down, and you'll notice the reaction in blue are the reaction species, and then in pink is, you can see a heat energy unit. You guys, this is kcal, kilocalories, that's a unit of heat. And you'll notice the difference here. In this case, look at this first equation. You'll notice the heat units on the reactant side. What that indicates is it's an endothermic reaction. When hydrogen and iodine come together, in order for hydrogen and iodine to come together to form hydrogen and iodine, it also requires heat energy. So heat energy plus hydrogen and iodine can form this, okay? But now look at the second reaction. You'll notice the heat unit is on the product side. What that indicates is that is an exothermic reaction. In this case, heat is absorbed. In this case, heat is released. What this is showing is when nitrogen and hydrogen combine together to form ammonia, not only do they form ammonia, but they also produce heat. Okay? So, we talked about causing a stress or a change in the system. So just imagine you have both of these reversible reactions are at equilibrium. Let's say we disturb it. For example, we can disturb it by adding another species, reactant or product. We can add more reactant or product. Okay? So now we want to predict what would happen to the equilibrium if we add some more to that closed system. So we'll show you a little example here.
When water is added to the tank.
So just imagine, okay? So we have these two containers of water at equilibrium. So then what we're going to do is we're going to disturb the equilibrium by adding more water. And just look at the system. What do you think when we add more water here, what do you guys think is going to happen? Okay, let's see.
When water is added to the tank on the left, the water moves from left to right. The level of water goes down a little on the left and up on the right. This is similar to adding more reactants to a reversible chemical system. The result is that more product forms because the forward reaction is favored until a new equilibrium is reached. We say the equilibrium has shifted to the right.
So this was representing the reactants. This was the products. It's at equilibrium. Let's say we added more reactants, and then you could see what happened. Water began to flow to the right. We'd say we call that the forward reaction. So there was an increase in the rate of the forward reaction. And you see the result was, even though there was this much change, because the water shifted this way, or there was a shift to the right, the result is it was as if you added less water than you actually did. That's what Le Chatelier would predict. And we could look at it.
When water is added to the tank on the right.
Now think about it. What if we had it on that side, on the product side? Wouldn't you expect the same thing,
the
just in
level of
reverse?
water goes up on the left and down on the right.
That was the change, but it results
This is similar
less of
to
a
adding
change.
more products to a reversible chemical system. They react together to form more reactants. We say the equilibrium has shifted to the left because the reverse reaction is favored until a new equilibrium is reached.
So we say shift to the left, reverse reactions favored. When we say shift to the right, the forward reactions favored. He says, I just joined this gym. Welcome aboard. Aren't you going to work out? No, I just wanted to check in on Facebook that I was here. I just cares about image. All right. So, guys, let's show this how it pertains to chemical reactions. So let's say we have this reaction here. Let's say we have an enclosed container. These are all gases. So, it always helps to have a drawing. So just imagine in this, you have hydrogen gas, you have iodine gas, and you have hydrogen iodide, right? And they're all in there. And then let's say we disturb it by, let's say we add more hydrogen iodide. So we now put more hydrogen iodide in there. The question is, what's going to happen to the equilibrium? Well, you guys should think about it. Now, if I add more hydrogen, wouldn't you guys agree there's going to be a lot more collisions now between hydrogen and iodine? What's the result? That's going to speed up the rate of the forward reaction. Remember, at equilibrium, the rates of the forward and the reverse are equal. But at least momentarily, now the rate of the forward is going to be, you guys see how I do a bigger arrow to the right, is going to be faster than the rate at which the hydrogen iodide is breaking up to form hydrogen iodide. So what's the result of adding more hydrogen? We'd say there's a shift to the right. And so what ends up happening? You end up producing more hydrogen iodide. You end up using up more iodine, right? Because now there's more hydrogen with which the iodine can combine together to form hydrogen iodide. We'd say there's a shift to the right. And you guys see what the result is. By shifting to the right, some of that added hydrogen now combines with the iodine to form hydrogen iodide. And so now even though you obviously are going to have now and then it's going to reestablish a new equilibrium. At the new equilibrium, you know what's going to be different? You're going to have more hydrogen than you had before, duh, because I added more hydrogen. You're actually going to have less iodine than you had before, right? Because now some of that iodine reacted and combined together with the additional hydrogen. And then what's the result of this? You're going to have more hydrogen iodide. That's what Le Chatelier's would predict. So if I add, the way you guys could look at it, if I add some more to one side, there's going to be a shift to the other side. And that's because it's going to increase the reaction rate. Okay, well, you guys could probably guess, if you're going to disturb an equilibrium, you could add a reaction species, or what else could you do? You could remove a reaction species.
When water is removed from the tank on the left, the water moves from right to left. The level of water goes up on the left and down on the right. This is similar to removing reactants from a reversible chemical system. Products will react to reform more reactants. The reverse reaction is favored until a new equilibrium is reached. We say the equilibrium has shifted to the left.
So you guys see what happened? So we removed a bunch of water, right? And so what was the result? We removed the water. The water's going to shift this way, and what happens? It ends up replacing some of the water, so then it looks as if there's less of a change than there actually was. That's what Le Chatelier would predict. And then it could go
When water is removed from the tank on the right, the water moves from left to right.
This was the change.
The level of water goes
shifts
down
to the
on the
right,
left and up
and now
on
it's
the
going to
right.
make it like less of a change.
This is similar to removing.
Okay. So, guys, let's just look at our scenario here. Once again, let's say we have a reaction at equilibrium. We have hydrogen molecules, iodine molecules, and hydrogen iodide. This is that first reaction, right? So then, let's say we take some of this out. Remove some of this. So we're going to disturb the equilibrium. And so let's say we take some out. So now look, because right, wouldn't you guys agree? Some of the hydrogen iodide molecules can collide together, and if they have sufficient amount of energy, that you remember the activation energy is the minimum amount of energy for an effective collision, it's going to break up into hydrogen and iodine. That's the reverse reaction. But now, if I have less hydrogen iodine, wouldn't you guys agree there's going to be less hydrogen iodide molecules with which to collide? Therefore, what's the result? Wouldn't you agree? Wouldn't you agree? The reverse reaction is going to now be slower, right, than it was before, because we have less hydrogen iodide to collide. And so, what is the result of removing hydrogen iodide? You guys look. So now, at least momentarily, the rate of the forward reaction is now going to be faster than the rate of the reverse reaction. Remember, which slowed down because we have less hydrogen iodide. So there's what we call a shift to the right, and what ends up happening? You end up shifting to the right. You end up replacing some of the hydrogen iodide that was removed. And so what's the result? So ultimately, and then what's going to happen? Eventually, what's going to happen? It's going to reach equilibrium again. But now at that new equilibrium, how are the concentrations of these changed? Well, obviously, if I remove some hydrogen iodide from the original, when I obviously have less. I'm going to have less than I had before because I pulled some out. But as a result of shifting to the right, what's going to happen to the amount of hydrogen now? Aren't I going to have less? And what's going to happen to the amount of iodine that I have? Isn't it? They're going to be less, because that's what results when the rate of the forward reaction now all of a sudden is faster. These what's happening? These are going to combine together and form this much faster than these are going to break up to form that. Okay. All right. So what do we see here? If I remove from one side, what would Le Chatelier's predict? There's going to be a shift to the right to replace some of that which was removed. Okay. All right. Another change that we could do to a system. Not only can we add a species, not only can we remove a species, we could also change the volume. But you notice this will only affect gases, right? When we're changing the volume of gases, and you can imagine, right, if you change the volume of gases, you're also going to change the pressure. So that's ultimately going to potentially affect the equilibrium. Okay. I'm gonna make a scenario here just so we can see what's going on. Okay. I want to do that. Oh yeah, guys, let's look at this scenario here. Okay, check this out.
The reaction of dark brown nitrogen dioxide gas to produce colorless dinitrogen tetroxide gas is an exothermic reaction.
Okay, so it's saying it's exothermic. So what does that mean? You guys, right? If you're doing it, it means as this reaction proceeds from the left to the right, it's going to produce heat. So basically, we have this reaction. So basically, I'm going to put the heat on the product side. Okay.
A sealed flask contains 3 molecules of nitrogen dioxide for every 1 of dinitrogen tetroxide, and the system is at equilibrium. If we then transfer the mixture to a flask with a smaller volume, NO2 molecules convert to N2O4 molecules, resulting in a net decrease in the number of molecules. In this way, the system compensates for the decrease in volume by a decrease in gas pressure.
Okay, so I don't know if you guys noticed that. So what they're showing is before, let's say it's in a closed system, right? The gas can't escape, so then a reversible reaction can happen. So some of the NO2 molecules are going to collide together and they're going to combine together to form N2O4, which is a larger compound. But then at the same time, N2O4 molecules can collide and then dissociate back into NO2 molecules. Well, what you saw was when we took the gas and we put it in a lower volume, so we decreased the volume. Okay, you guys think about what's the effect of decreasing the volume? When you have the same, think about it, you have a certain amount of gas and now you put it in a smaller volume. Aren't you going to increase the pressure, right? Because you have the same amount of gas molecules that are now in a more confined volume, and so that's going to increase the rate of collision. It's going to increase the pressure. The Chatelier's principle, you guys remember, predicts it's going to shift in such a way to minimize the change. Well, what was the change we ultimately did? By decreasing the volume, we increase the pressure. Le Chatelier's principle is going to predict that it's going to try to lower, it's going to shift in such a way to lower the pressure in response to the high pressure, okay? Lower pressure. So now, this is where we need to predict, okay? Which way would the equilibrium shift? Well, if it's going to shift in such a way to reduce the pressure, you guys got to think, which arrangement of atoms ultimately, think about it, what ultimately results in more pressure? More gas molecules or less gas molecules? When you guys agree, the more gas molecules you have in a confined area, the greater the pressure. But remember, it's going to shift in such a way to lower the pressure in response to the increased pressure. Remember, when we decrease the volume, we're increasing pressure. Le Chatelier's predicts it's going to shift in such a way to reduce pressure. It can accomplish that by favoring an arrangement of atoms that results in less overall gas molecules. So here's how you tell. So remember, these are both gases. So this only pertains to gases. So when you guys have a reversible reaction, you only look at the gases, and both of these are gases. So if you look, if the nitrogen and oxygen atoms arrange like this, how many gas molecules result? 2. But if those same atoms arrange themselves like this, how many gas molecules result? Only 1. Which arrangement of atoms results in less overall gas molecules? When you guys agree? This one. So what's the result? There's going to be a shift to the right. Thus, you guys see what end up happening. We end up producing more N2O4, but ultimately that results in less overall gas molecules, which results in less pressure, which is what Le Chatelier would have predicted would have been the response to the increased pressure due to the lower volume. So the result is there's a shift to the right. So let's just kind of look at it this way, guys. Let's go with this reaction right here. Nitrogen and hydrogen combine together form ammonia, but remember it can go both ways. Let's say we take that, so we have a certain amount of nitrogen, hydrogen, and let's say it's in equilibrium. But then, let's say the effect is, we take those same gases and we put it in a smaller volume. Now, wouldn't you guys agree, what we've done is, we've increased the pressure, right? Le Chatelier predicts it's going to shift in such a way to reduce the pressure. So then, what's going to result in less pressure? Wouldn't you guys agree? Less overall gas molecules. So, upon doing that, the question is, we look, which arrangement of atoms, the reactant side or the product side, results in less overall gas molecules. So you just count. Look, these are all gases. So look, if arranged like this, I'd get one of these and three of these for a total of 4. I just add them together, 4. I'd have a total of 4 gas molecules, right? But if those same atoms arrange themselves like this, how many gas molecules result? Only 2. So you see the product side results in less overall gas molecules. That's what I would expect to happen. I would expect there to be a shift to the right, meaning the forward reaction is now going to be faster than the rate of the reverse reaction. And what's the ends up being the result? I end up producing more ammonia gas. That would be the result of decreasing the volume. Okay, one last thing that we can do, and I bet you guys could have guessed this. What's one thing we can do another thing we can do to change the system? Not only add, not only remove, not only change the volume, but we can change the temperature. Changing the temperature. Okay, whenever you change the temperature, guys, what you want to focus on in this case to know which way the equilibrium is going to shift, you always want to look at the heat unit, and you want to see on what side is the heat unit located. Is it, for example, an endothermic reaction where the heat is absorbed in the forward reaction, or is it an exothermic reaction in which heat is given off in the forward reaction? So once again, we'll go back to this.
The reaction of dark brown nitrogen dioxide gas to produce colorless dinitrogen tetroxide gas is an exothermic reaction.
Okay, so it's an exothermic reaction, so I'm going to put that up here. So it's an exothermic reaction. So you notice if it's exothermic, I'm putting that heat on the product side. That means heat's being produced as I proceed from left to right.
You are right. We could show heat as a product.
Okay, and so this is what's different. In fact, you guys, you see the brown gas, NO2, you guys, that's actually the same, a lot of the gas that comes out of your car's exhaust pipe, that's a pollutant, right? You guys know if you're at the border, right, and you have to wait at the borderline, you can see it's a lot more smoggy there, right, as cars are idling to get across the border. A lot of that is the brown NO2 gas. So, if you guys were looking at a container that had both NO2 and N2O4, you could figure out which side is favored basically by seeing does the container look more clear or does it look more brown? If it's more brown, obviously the equilibrium is dominated by the NO2. If it's more clear light, you guys see it's kind of a yellowish. That would be kind of like a clear, and you can see it's kind of yellowish, indicating that there's both N2O4 and NO2 molecules present.
In a sealed flask, we have nitrogen dioxide and dinitrogen tetroxide. As the temperature is raised, the color of the gas darkens as more of the brown nitrogen dioxide gas is formed.
You guys see what they did? So they had this on ice, right? They had it on ice, and you saw it was more yellow on ice, indicating you probably had more N2O4, that the right side of the equation was favored, that there's a greater concentration of N2O4 than NO2. Then, obviously, you guys, it was on ice. Obviously, you just let it sit. What's going to happen to the ice? It's going to melt. And as it melts, what happens to the temperature? When you guys agree, the temperature goes up because there's less ice surrounding. So as the temperature went up, you guys notice what happened to the color of the gas inside? It became more and more brown. Obviously, you guys can see which way there was a shift to the left. And you guys look, this is kind of, you can predict this. Look, if you look at it from Le Chatelier's perspective, you could look at heat like a product, right? You see NO2 combines together to form N2O4 and also heat. Well, we saw as the temperature increases, you know, when you increase temperature, it's kind of like you're adding heat. You know? So it's like you're adding heat to the system, right? And if you're adding heat to the system, what do you guys expect? You guys remember what we said, if you're adding to one side, you're going to expect a shift to the other side. And it should make sense. So basically there's a shift to the left, thus producing more NO2, and that explains why it's more brown as the ice was melting. And you can look at it this way too, guys. If you add more heat, because look, for N2O4 to produce NO2, what else does it need? It needs heat, right? Both of these together forms this. If you have more heat, what you're going to do is you're going to speed up the rate of the reverse reaction. That's what we mean when we say shift left. That for a time, the rate of the reverse reaction is faster than the rate of the forward, and then what's the result? We end up producing more NO2, and we end up using up more N2O4. And you see, according to Le Chatelier's, right, the more heat I'm adding, it's going to shift in such a way to reduce the amount of heat added, because some of that heat is going to be used to further the reverse reaction.
Let's look at a particle view of this reaction in our virtual laboratory.
So you guys see originally, look at the background, they're kind of showing it yellowish, it's kind of like clear. And why is it clear? Because more of the molecules are N2O4. See, they're N2O4. Now there are some NO2s, but it's more N2O4. Now as the temperature increases, as we add heat, the rate of the reverse reaction speeds up, and what's the result? We end up producing more NO2, and we can see it's more brown.
So if heat is treated just like a product, when heat is increased, the reaction shifts to the left.
Says, you're a dog, Fang. How could you understand the complexities of true love? The dog says, trust me, no. The underwear model in today's Sears ad, that's not your soulmate. I thought they were in love. Okay, guys, one last thing you can do that can possibly disturb the equilibrium is adding a catalyst. Now, I'll say this though, guys, it's really important. When you add a catalyst, remember what a catalyst does? It speeds up a reaction rate by lowering the activation energy. Basically, it's going to arrange the molecules in such a way, or bind the molecules in such a way, so they can have a proper orientation, so that way when they collide, they don't have to collide with nearly as much energy. Therefore, the result is you're going to have a greater percentage of those collisions are more effective. The result is it speeds up the reaction rate. What it does not do, though, this is important to note, it doesn't shift the equilibrium. If I add a catalyst here, I'm not going to produce more HI, and I'm not going to produce more hydrogen iodine. All a catalyst does is it causes the reversible reaction to reach equilibrium faster. It's just going to reach equilibrium faster, but it's not going to shift the equilibrium either to the left or the right. And I think that is it for today, guys. Thanks for hanging out with me. Until next time. Bye.